Okay, students, today I want to look at how to find the derivative of an inverse function. And I also want to look at how to find the limit using L'Hospital's rule. So, what do you want to do today? We want to find the derivative of the functions of the form. So now we can even see of the inverse functions. So e.g., let's take, it could be f of x, which is equal to sine inverse of x. So if somebody gives you this type of function, how do you get the derivative here? That's what we want to look at. And also, we also want to evaluate the limit of the form. The limit as x goes to 0 of e to the x. It may not be exactly like this, but this is the kind of the function. Here we have x squared. In fact, here I want to say as x goes to infinity to make it more interesting. So how do we get the limit here? And you can see in this form we have the form infinity, because if you take e to the power x, you substitute large value, you get infinity, and you substitute large values for x in x squared in the denominator, you also get another infinity. So that's infinity over infinity. And we said this is one of the indeterminate forms. So how do we evaluate that limit? That's what we want to address today. So let's get started straight away. So inverse function derivative. And like before, let's start with an example and try to extend afterwards to some more general knowledge now. So let's start. So let's start with the same function that we had at the beginning, with f of x, which is equal to sine inverse of x. So one thing to note here is that when you talk about sine inverse of x, is different from 1 over sine of x. So be careful about this portion, that this one is the reciprocal, this one is an inverse function. So the two are in general different. So you can't equate the two. Another thing which we know how sine inverse looks like. So we know it looks somehow like that. If I were to draw, so we know that this point here is pi over 2, and then this point here is minus pi over 2. So this is how our sine inverse looks like. And for this, what we are going to do now, bear in mind that for sine inverse, we are focusing on the range minus pi over 2 being less or equal to y, which is less or equal to pi over 2. We'll come back to this later, but let's go back to the function. So first let f of x to be equal to, effectively let y to be equal to f of x, which is equal to sine inverse of x. So we're interested here in y, so which implies y is nothing but sine inverse of x, and straight away we can solve for x. Then we know that this is equivalent to say sine y is equal to x. At this stage, we are now ready to take the derivative. Let's take the derivative both sides. So we have d dx on the left on sine of y, and on the right we have to do the same. D dx, the function on the right is just x, which we know here will just get 1. But what happens on the left here? On the left, be aware that we are differentiating with respect to x, but we have a function of y. We need to apply chain rule here. So we have d dy of sine y, then we need to multiply that by dy dx. That's the chain rule. And then we still have the right hand side be equals to 1. And if we do that, on the left you get nothing but cos y times dy dx, and that is equal to 1, which implies that now we can write dy dx as nothing but 1 over cos y. Good news here, up to here. But now let's take a bit of break, because somebody can decide to stop here. But here, for you to evaluate dy dx, you are required to know the y value, which can be a little bit complex to get. So it's easier if we have dy dx as a function of x. Whenever somebody gives you x, you can be able to get dy dx. So let's see if we can get to that point. What we know. So what we know. But we know from the algebra that cos squared of y plus sine squared of y is equal to 1. And we can simplify this to have cos squared of y to be equals to 1 minus sine squared of y. And we can even go further and solve for cos x, cos of y. Cos of y in this case becomes plus or minus square root of 1 minus sine squared of y. Interesting. So remember, if you go back, remember what is sine y? Sine y is nothing but x here. But here we have f cos y in terms of sine y squared. So that means here where we have sine y, we can replace it with x here. We can pick our x and bring it here and then replace it with x. If we do that, we have nothing but plus or minus square root of 1 minus x for sine, but sine is squared, so we'll have x squared. This is what we have. And we want to replace that for cosine here. One thing to note here, which I highlighted at the beginning. I highlighted that the graph of sine is given by this, as we see, but I also highlighted the range here which we are interested in. And now with this range, the argument is that range allows us to take the cosine value, where we can say cos y. Now in this case we take the positive value only for that range. Go and find out. I'm leaving that for you to go and think about it. So we can even say for y, that is between minus pi, which is between pi over 2, where the inverse function exists. So this is a very important result, but specifically we want to pick this portion and then take it and plug it here for cosine. Therefore dy dx becomes nothing but 1 over square root of 1 minus x squared. That's beautiful. This is the inverse for sine. The inverse, this is the derivative of the inverse sine. So that's the derivative of the inverse sine function. What about cosine? What about tan? What about others? I think you can follow the same procedure. You'll still get something, some expression for each of those cases. But for now, I need to generalize, because here we considered just sine inverse of x. So let's extend a little bit to make it a little bit complicated to see. So what can we say here? We can say in general, let's say, suppose f of x is given by sine inverse of g of x, for argument's sake. So let's put g of x. Then what do we do? The first thing you can do, you can then let u to be equals to g of x to get let u to be equals to g of x to get what? To get du dx to be equals to nothing but g prime of x, and now it means f prime of x. Now we can apply chain rule. So if we are supposed to differentiate d of dx of that function, which is sine inverse of u in this case, so we can apply chain rule to have d du, and then you still have sine inverse of u, and then we multiply by du dx. But we know what is the derivative for this one, which we've just found previously. So it leaves us with nothing but 1 over the square root of 1 minus u squared multiplied by what? Du dx. Du dx, we just compute it here, so it's nothing but g prime of x. This is a very important part. In fact, what is important is the whole of this expression is very important, because now it means even if f of x now becomes more general in this form, we can still find the derivative of that. and we know chain rule, we can find this for any. So this is for sine, then we went to the general part. So I'm leaving for cosine for you to do for cosine. Once you know cosine and sine, then you can derive others from the two. I'm just leaving that part for you. Please work it up and see. So straight away, I want to move a little bit towards L hospital, but let me start with types of indeterminate form. Indeterminate forms. So far, remember, we have seen 0 over 0. That's the one that we have seen, and probably we have met at one stage plus or minus infinity over plus or minus infinity. We want to introduce more indeterminate form. Remember, this indeterminate form, they come when you are trying to evaluate the limit. Then immediately you see that one of these possibilities, that is the form of the limit. So you know that once you get that, you need sometimes to do a little bit of work. So we introduce 0 multiplied by plus or minus infinity. This is another one which is very difficult to conclude, because when we are here, remember, these are just forms. It's not exactly 0. It tells you that the function approaches 0 as you take the limit to that point. But if you have one function that approaches 0, the other one approaches infinity, it's very difficult to conclude that it will be 0 at the end of the day, or it will be infinity. It depends who is the stronger of the two. If infinity is very strong, they may both end up at infinity. Or if the one that pulls towards 0 is very strong, they may end up at 0. So it's a complicated situation to conclude immediately. Therefore, let's look at another one. Another one could be the one where we have 1 to the power infinity. So this is another indeterminate form. One function, as we take the limit to test, we find that it pulls towards 1, and then the exponent of that part pulls to the infinity. So the question is, what is your answer? It becomes very hard to conclude again. So there is another one where you have 0 also to the power 0. So they are both pulling towards 0, but the other one is an exponent. It's another indeterminate form here. We have another indeterminate form of infinity to the power 0. And then we have the last one, which I want to mention now, which is infinity minus infinity. The last one, temptation is to say this will give 0. But in most cases, remember, infinity is just a large number. So this could represent a large number, which is not necessarily the same large number that side. So it's very difficult to say this will go to 0. Infinity just represent that this thing gets large and large and large. So we can't exactly fix it to a number so that we subtract the 2 to say this is 0. So we can't conclude there. We have to think of some ways to do. So one thing to mention here, L hospital will depend more on these two. Once we have the first two, it's going to apply directly. But the others here, you may need to do some work before the L hospital applies directly. That's one thing to take home. So which brings us to L hospital's rule. L hospital's rule. So the L hospital rule. So the L hospital's rule. So what are we doing? We say suppose that we have one of the following cases. They don't need to be both, one of them is fine. So what are these cases? You could have the limit as x goes to a of f of x over g of x being of the form 0 over 0. Or we could also find another form, which is the limit as x goes to a of f of x over g of x being equals to, it could be plus or minus infinity over plus or minus infinity, both one of the two is fine. So once we have these two, that's where L'Hospital is going to apply. If we have this one or this one, so where here a is just a real number that we can pick, or it could also be plus or minus infinity. Then the limit as x goes to a of f of x over g of x will be given by nothing but the limit as x goes to a of f prime of x over g prime of x. So L'Hospital says once we have these two forms, either this or this one, straight away you can take derivative of the numerator to get f prime, and then take derivative of the denominator to get g prime, and then you will get the same value of the limit. And this is very good. You will see that is going to simplify our work nicely. So what normally happens here, most students used to confuse this with quotient rule. This is completely not a quotient rule. In fact, it's even simpler than quotient rule, because quotient rule you have to work very hard. Here you are differentiating the numerator and denominator separately and putting the result there. So you don't need to work too hard. So don't make it a quotient rule as time goes on. But to take the concept home, let's look at examples. So that at least you are clear. So the question says evaluate the following. And how do you evaluate the number a? Let's say you have the limit, the one that we started with at the beginning, as x goes to infinity of e to the x being divided by x squared. And then number b, you have the limit as x goes to infinity of x raised to power 1 over x. And then number c, we have the limit as x goes to 0, but from the positive side of x ln of x. So we have these three examples. So let's demonstrate with these three examples how you go about the limit. Let's demonstrate using these three examples. So solution. So now let's start with the first one. Number a, we have the limit as x goes to infinity of e to the x over x squared. So first we need to test what form is this one. So let's test the form. Let's try to plug in infinity at the numerator you will get infinity. You try to plug in the denominator to look at the behavior of the function in the denominator. You'll find that it goes to infinity. So L'Hospital can apply here. That is the first thing you need to do. So we can start saying, therefore, the limit as x goes to infinity of e to the x over x squared is equal to the limit as x goes to infinity, then now of dx of the numerator expression, which is e to the x, divided by dx of the numerator expression, which is nothing but x squared. So if you do that, what do you get? You get the limit as x goes to infinity. The numerator is just the same as it is. You try to take the derivative of e to the x to get the e to the x. Then in the numerator get 2x. Quite good. But are we ready? Is it possible to substitute now? Let's try to check. You try to test. Again, you put infinity on the numerator. You find that it still goes to infinity. You try to put infinity in the denominator, you find that it still goes to infinity. So you still have infinity over infinity. Oh, good. So you are still safe to apply L'Hospital again. So we can say the limit as x goes to infinity of e to the x over 2x will be equal to nothing but the limit as x goes to infinity of the derivative of ex over the derivative of 2x. But now what do you get from those derivatives as x approaches infinity? So you take the derivative of the top, it still remains as e to the x. The denominator, you get just 2. Very good. Now you try to test again before you move forward. So let's do the test. If you test the numerator, you get infinity, but the denominator is 2. So we can apply L'Hospital here. And that's the answer, because straight away we get infinity. So that's the limit. That is our limit. That's the answer to our problem. So you can see that in some cases you may need to apply the L'Hospital twice, because the new expression that you get after applying the first or L'Hospital still agrees that you can apply. The form is still infinity over infinity or 0 over 0. So depending on the problem, you may need to apply it twice or 3 times. And this one was nice because it was straight away from the beginning. It was allowing us to use L'Hospital. Let's look at number B. What about number B, where we have limit as x goes to infinity of x to the power 1 over x. And in this case, if we try to check the form here, you'll find that if we do that, here on the base you have infinity, that's x. X can grow and become very large. On the exponent we have 1 over x. So if we put a large number here for x on the exponent, you'll have a number that goes to 0. So you have a form of infinity to the power 0. Interesting, but bad news now that it's not where L'Hospital can apply directly. Meaning we need to do a little bit of work before we can apply L'Hospital in this case. But don't worry, let's try what we can do. So what we can do now, you can say let your y to be equals to, you try to simplify your work to equals to 1 over x. We hope that if we can bring 1 over x down here, we may get a simple expression. And the only thing to do that is to apply logarithmic on both sides, or ln on both sides. So to make it simpler, let's apply ln, get ln y, and then on the right we get ln of x, but x is raised to the power x. Now you can see that the right hand side becomes 1 over x ln of x. So it's somehow good news, which implies ln of y is equal to what? Ln of x being divided by x. That is very interesting. So now you can see, if we were to test here, let's take the limit on both sides to see. Let's take the limit on both sides, the limit. But one thing you should remember is that this is a new problem. It's not the problem that was asked. We have now modified the problem to get the new problem, but it can help us to solve the original problem. So the limit as x goes to infinity of ln of y will be equal to the limit as x goes to infinity of ln of x over x. Now if we test on the right hand side here, let's do the test. The top part, ln as x goes to infinity, it will blow up to infinity, and then divide by the denominator, x will just go to infinity also. Bah, good news. L'Hospital. Now it can apply. Beautiful. Beautiful. Now we can apply L'Hospital. Although it's a new problem, but we can apply L'Hospital. Therefore, we can say the limit as x goes to infinity of ln of x over x will be equals to the limit as x goes to infinity of the derivative of the top by L'Hospital over the derivative of the denominator by L'Hospital, which gives us nothing but the limit as x goes to infinity. The top you get just 1 over x, the denominator just get 1, so you are safe. Anyway, you still have, which implies now, which is equal to nothing but the limit as x goes to infinity of 1 over x, and here you can see as x gets very large, this expression goes to 0. The limit of this new function we have created, we have modified, is 0. Let's see if this new function can now be able to move back to the original function. So, but the limit as x goes to infinity of ln of y is equal to the limit as x goes to infinity, remember, of 1 over x, which is 3 equal to 0. This is the situation we have now from the previous. So, and here on the left we can pass the limit into the function so that we have ln of the limit of x as x goes to infinity of ln of y of y. So we have the limit of y as x goes to infinity, we close. On the right we just have 0, which is good for now. Now we can be able to say the limit as x goes to infinity of y, then we can take the reciprocal on both sides, then we have being equals on the right e to the power 0. So you can raise everything to e, and then ln will just, you'll be left on the left, will be left with limit as x goes to y of y, then on the right will be left to e to the power 0, which is nothing but 1. This is good news. So remember, what is y? Now remember from where we learned that y is equal to x to the power 1 over x. If you go back, we'll find that we exactly let y to be like that. So it means actually the limit we have just found, which is the limit of y, which implies that the limit of y as x goes to infinity of y is the same as finding the limit of the problem that we're looking for as x goes to infinity, which is x to the power 1 over x, which is nothing but 1. There we go. There we go. We've got it. Beautiful. Let's look at number C, the last one. It's of different nature too. So number C, we want to find the limit as x goes to 0 but from the right of x ln of x. So let's first, as usual, check the form. The form in this case, you put 0, you have 0 on the left, but if you approach 0, you have something that close to 0, but let's represent it with 0, and then it is multiplied by what? If you check here on ln, you try to put something that is very small that goes to 0, the ln will approach minus infinity. I hope you can test that when you're alone. So this is the form, which is one of indeterminate form. So with this type of form, the trick is different from the previous one, because if you look at this type of form, if we can take 1 over a function that goes to infinity, you are likely to get 0 over 0. So if we can turn this form around such that we have 0 over 0, or you can turn it around by this function which goes to 0, you say you divide by 1 over something that goes to 0, which will go to infinity, so you'll have minus infinity over infinity. Then you have achieved your aim. Meaning, if the first case, you can transform this form with the fact that this thing we can divide by, let's not even say this one. Let's talk in terms of functions. So let's say you have f here which goes to 0, and then we are representing this first portion. Now you are dividing it by 1 over some g which goes to minus infinity. And you know when you divide this, it's the same as in this form, multiplying. So you haven't changed anything because the first one goes to 0. If you turn this one upside down, you are back to 0 times minus infinity. But you can put it in this form. But in this form, which is the new form now, you have achieved 0 over 0. Look at it properly. You have achieved 0 over 0 somehow, because the denominator as g goes to minus infinity, it goes to 0. So f goes to 0. So you have 0 over 0. The other way to treat this form, you could also, let's say you keep the top, let's say g, let's start with g in this case, so that we are somehow consistent. So let's start with g. So let's say g of x still goes to minus infinity. Now you decide to put 1 over f that goes to 0. If you do this part, this one, now you can see now it takes us to the form of what? Minus infinity, possibly over infinity or minus infinity. But it's still an L'Hospital. So we want to achieve one of these two. One of them will make our life simpler. One of them may make our life hard, that we differentiate all the time and then you give up. So you must be able to choose wisely here so that you don't get into trouble. But let's get to back to the example. Okay. So the limit as x goes to plus infinity. Let me just put this part aside here. of from the right of x, ln of x can be written as the limit as x goes to plus infinity of ln of x over 1 over x. Be aware that this function is still the same, but what have we achieved? Now we have achieved to make it 0 over 0. This portion, oh no, we haven't achieved that one. We have achieved to make it minus infinity over infinity. So it comes, we have achieved to make it this one. Let's look at why. If you check the top, the numerator, this portion as x goes to 0 from the right, it will approach minus infinity. But this part will approach plus infinity because it's 1 over something that gets close to 0. So you're dividing by something but from the positive side, so it will approach plus infinity. So we are exactly on this form. Bear that in mind. Therefore, L'Hospital can apply now. So now we can say the limit as x goes to 0 from the right of ln of x over 1 over x will be equals to the limit as x goes to 0 from the right of the derivative of the numerator divided by the derivative of the denominator, which is equal to what? If we take the derivative of the numerator, they get the limit of ln. Remember, if we take the derivative of ln, you just get 1 over x, which is the numerator, and then you take derivative of this one. You can work this one alone. You can use quotient or turn it into a function that can apply power rule straight away. But anyway, you should get minus 1 over x squared. Minus 1 over x squared, which is much better. And we go to the next step as x goes to 0 from the right. Then you have, if you simplify this function, you'll have nothing but x. And now it's very friendly. Now you can plug in a 0, then your final answer for the limit becomes 0, which is this part. Wow, that's very interesting. So that's very interesting, and it has given us a new way to look at this indeterminate form. So what I want you to try and see that you might get into a danger. When you're at home, go for this form. That means you modify this function to come to 0 over 0. So you can put that as x being divided by 1 over ln of x. That, because x will go to 0 and then ln will go to minus infinity, but you're taking 1 over that will go to 0 over 0. So please, when you're at home, try that and see if it makes you work very, very hard. But I've chosen this one and it gave us the good answer. That's why I was saying, once you get to this form, you may need to choose wisely. Otherwise, you may differentiate for the rest of your life. But let's stop it here, and then now let's recall what we have learned today. We look at how to differentiate the inverse function, and then we started with a simple function of sine inverse of x. Then we went further to complicate the function to say, suppose now you have sine inverse of g of x, which is more general. Then we applied chain rule, we're able to get the results. We introduced a number of new indeterminate forms. And then after introducing a number of new indeterminate forms, now we introduced L'Hospital's rule, and we applied L'Hospital's rule into 3 examples. So by now you should be very good with L'Hospital and you can handle any problem in the tutorial. So this marks the end of the first part where we are ready for test 1. So this will be included, whole of this up to here will be included in test 1. So now we are ready for test 1. The next thing we'll look from next week will be applications of derivative, but we stop here with limits and all that, the first part. Good luck.